All right, let's get right into it. We write code in these languages that, they look a lot like English, but the processor, the actual brain of our computer, that's just a piece of silicon. It only gets electricity. So how in the world does one talk to the other? That's the big mystery we're going to crack today.
Yeah, this is the real puzzle we're going to unravel. How does your creative, abstract idea, the code you write, turn into a bunch of real, physical actions inside that chip? That journey, from your keyboard to the silicon, it's really all about translation, and it's a fascinating one.
So the first thing you have to get your head around is this massive language barrier. I mean, it's huge. We're over here expressing these complex, nuanced ideas in our fancy programming languages, but the computer, its native tongue is, well, it's incredibly simple, almost primitive, really.
And that native language, it's called the instruction set. The best way to think about it is like a vocabulary list for the hardware. But here's the catch. It's a tiny vocabulary, like really, really small. It has 0 words for calculate my mortgage or render this cool video. Nope. All it knows are these brutally simple commands like add these 2 numbers or move this little piece of data from here to there. That's it.
Okay, so how do we bridge that gap? Well, the very first step is to take our big, complex thoughts and just shatter them into tiny little pieces that fit into that simple vocabulary. And the tool that does this incredible job is called a compiler. Its whole purpose in life is to be our translator, turning one of our complex sentences into many, many simple ones for the machine.
Let's look at a real example. Check out this single line of C code. Now, for you and me, this is easy, right? It's one clear idea. Add G and H, add I and J, and then subtract the results. Simple. But for a computer? Whoa, no way. This is way too much to handle all at once. It has to be broken down.
And here's exactly how the compiler does it. See, it takes our one line and turns it into 3 separate simple instructions. First, it adds G and H, and it sticks that result in a temporary little scratch pad it calls T0. Then it does the same for I and J, and puts that result in another spot, T1. And only then, as the very last step, does it subtract those 2 temporary results to get our final answer, F. So one complex human thought just became 3 dead simple machine steps.
And this whole process reveals a really core design principle for modern processors. Simplicity favors regularity. By forcing everything into this super simple, super regular format, always take 2 things, do one operation, put the result in a third place, the hardware itself can be made a lot simpler. And why does that matter? Because simpler hardware is almost always faster hardware.
Okay, that makes sense. The computer is just doing simple math one step at a time. But wait a minute. Where are these numbers G and H actually coming from? Where do they live? For the processor to do any work, it has to get its hands on them. And it turns out the computer basically has 2 totally different kinds of storage.
And this analogy nails the difference. First, you've got registers. Think of these like a tiny workbench sitting right next to the processor. It's incredibly fast, but you can only fit a handful of things on it. In this example, just 32 little numbers. Then you have main memory. This is like a giant, sprawling warehouse. It can hold millions, even billions of items, but it's so much slower to go all the way out to the warehouse, find what you need, and bring it back to the workbench.
And this leads us right to our second big design principle: smaller is faster. It's a golden rule in hardware. That tiny workbench, the registers, the whole reason it's so small is so it can be lightning fast. And this is key. The processor does all of its actual thinking, all of its work, right there on that workbench. Nowhere else.
So this creates an unbreakable rule. The processor absolutely cannot do math on data that's still sitting out in the warehouse. It's just not possible. If you want to work on something, you first have to issue a load command. That's the instruction that says, hey, go get this thing from the warehouse and bring it to my workbench. Then, once you're done tinkering with it, you use a store command to send the final result back to the warehouse for safekeeping.
All right, let's see how this works in a real piece of code. Here we've got a line of C that uses an array. Now, arrays can be huge, right? So they definitely live out in that big warehouse, the main memory. And what we want to do here is grab one element from the array, A of 8, add the value of H to it, and then store that new results back into a different spot in the array, A of 12. And check out the compiled code. It's exactly what we just talked about. First, you see that LW? That stands for load word. It's the command to go to the warehouse, grab the value of A of 8, and put it on our workbench in a register. Then, and only then, the add instruction happens, right there on the workbench. And finally, SW, store word, takes that finished result and sends it back to the warehouse, putting it in the right spot for A of 12.
Okay, so we've got math and we've got memory. That's a good start. But real programs are more than that, right? They have to make decisions. They have to choose. So how does a processor, this simple machine, handle something like an if-then-else statement? How does it decide which path to follow?
You know, the way this works is actually really clever. When we write an if statement, we think pretty straightforwardly. If this thing is true, then do this. But the compiler, it often flips that logic completely on its head. It finds it's way more efficient for the hardware to think, you know what? If the condition is false, I'm just going to skip way ahead to the else code. If it's not false, well, I'll just keep on trucking with the very next instruction.
And you can see exactly how that plays out in the compiled code. The very first instruction is BNE, that's branch if not equal. It checks if I and j are different. If they are different, it immediately jumps all the way down to the code labeled else. But if they're the same, it does nothing. It just falls through to the next line, which is the add for the if block. And then right after that, you see that little j for jump? That's a crucial little instruction that makes sure we leapfrog over the else code so we don't run it by accident. It's a really elegant way to create two different roads from one single path of instructions.
Okay, we are so close. We've followed the trail from high-level C code all the way down to these simple text commands like add and BNE. This stuff is called assembly language. But, and this is the big reveal, this is still not the real language of the computer. It's another layer of abstraction for us humans. We're about to peel back that final layer and see what the machine actually, truly sees.
Right. This is the crucial takeaway. These words, add, LW, BNE, they're just helpful nicknames or mnemonics that we use. They're for us, the programmers. The processor has no idea what add means. It can't read. It only understands one thing, patterns of electricity, high voltage and low voltage, which we represent as ones and zeros, binary.
So let's do it. Let's take an instruction we're already familiar with, add $T0, $S1, $S2, and let's do the final translation ourselves. We are going to turn this line of text into the raw 32-bit number that the processor actually understands and executes.
Now, to do this, we need a blueprint, a kind of decoder ring. For this particular type of instruction, the MIPS architecture uses what's called the R format. It's basically just a template that says how to chop up a 32-bit number into a bunch of smaller fields. And each little piece of our text instruction, the operation itself, the source registers, the destination register, each one has a perfectly assigned slot in this blueprint. And here it is. This is the aha moment. All those names we've been using, they're just aliases. To the processor, $S1 isn't a name, it's just number 17. $S2 is 18. $T0 is 8. Even the command add is just a code, a specific combination of numbers that go into the op and funct fields. When you get right down to it, absolutely everything is just a number.
So when you take all those numbers, convert them into binary, and then slot them into the blueprint, you get this long string of 32 ones and zeros. That is what add $T0, $S1, $S2 actually looks like to the machine. This is it, the true language of the computer. It's not words, it's not symbols, it's just a sequence of bits that physically flips the microscopic switches deep inside the processor. So when you just stop and think about that for a second, it's kind of mind-blowing. Everything you do on a computer, every single click, every swipe on your phone, every frame of video you watch, it's all just the result of the processor executing millions, even billions of these incredibly simple instructions, one after another, at blinding speed. It's this staggering, beautiful complexity, all built from the simplest possible foundation. And it's all just hidden right there, in plain sight. It really makes you wonder, doesn't it? What other amazing complexity is hiding just beneath the surface of the world around us?